Hello everyone, I am Harika Shinde from Institute of Aeronautical Engineering. I am from second year from Computer Science and Engineering branch from B section. Today I am here to share and present my AAT concept video of a course Design and Analysis of an Algorithm. My topic is searching techniques in a design and analysis of an algorithm. So let's begin. So first, what are searching algorithms? Searching algorithms are designed to check for an element or to retrieve an element from any data structure where it is stored. Based on type of a search operations, these algorithms are generally classified into two categories. They are sequential search and interval search. First, let's see what is sequential search. In this list, the list or array, the list or array is traversed sequentially and every element is checked. For example, linear search, interval search. These algorithms are specifically designed for searching in sorted data structures. These type of searching algorithms are much and more efficient than linear search as they repeatedly target the center of search structure and divide the search space in half. For example, binary search. Types of a searching techniques. Even though there are many types of a searching techniques in design and analysis of an algorithm, some of them are linear search, binary search, interpolation search, exponential search, and Fibonacci search. First, let's see about linear search. A simple approach is to do a linear search is start from the leftmost elements of array and one by one compare x element. X is the element that is we need to find with each element of an array. If x matches with an element, return the index. If doesn't match with any of the elements, return -1. Time complexity of an above algorithm is big O of n. Linear search is rarely used practically because other search algorithms such as a binary search algorithm and hash tables allow significantly faster search comparison to linear search. So the time complexity of an algorithm is big O of n. Linear search is rarely used because other such algorithms such as binary search algorithm and hash tables allow significantly faster searching comparisons to linear search. Here is a picture which shows the algorithm of a linear search. For example, if we want to find an element of a 20, first is it checks and match with every element of a array. First, if it checks with an element of index 0, 10. If it doesn't match, it goes to 50, 30, 70, 80, and 60. Here in index 6, it matches with an element. So it simply retains the index number 6 and returns the number 20, that is element found. Next thing, binary search. Binary search algorithm. The basic steps to perform binary search are begin with the middle element of the whole array as a search key. If the value of a search key is equal to the item, then return an index of a search key. Or if the value of a search key is less than the item in the middle of the interval, narrow the interval to the lower half. Otherwise, narrow it to the upper half. Repeatedly check from the second point until the value is found or the interval is empty. Time complexity for binary search is big O of log n, and auxiliary space complexity is also a big O of log n. So binary search algorithm can be implemented in two ways. They are iterative way and a recursive way. Recursive method. Here it is a picture which shows the algorithm of binary search. For example, if we want to find a element 23 here in the list, so we first will check and compare it with the middle element. Here, the middle element is 16. So we compare with the 16 where a 23 is greater than 16. So we take to the second half. We compare there and we compare it with the second half elements. So in various steps, we repeat the steps, and at last, in a round 5, we found an element 23. We retrace the index number. That's it. Next, interpolation search. The rest of interpolation algorithm is same except for the partition logic. Algorithm in a loop calculate the value of a position using the proposition formula. If it is matched, return the index of the item and then exit. If the item is less than the array of a position, calculate the proposition of the left subarray. Otherwise, calculate the same in the right subarray. Repeat until a match is found or the subarray reduces to 0. And the time complexity for interpolation search is big O of log 2 of log 2n for an average case and big O of n for the worst case when items are distributed exponentially. Space complexity are big O of 1. Now, exponential search. Time complexity here is big O of log n. Auxiliary space complexity. The above implementation of a binary search is recursive and requires big O of log n space. With iterative binary search, we need only big O of 1 space. Applications of exponential search. Exponential binary search is particularly useful for unbounded searches where size of array is where size of array is infinite. It works better than binary search for bounded arrays and also when the element to be searched is closer to this first element. Next, Fibonacci search algorithm. Let the searched element be X. The idea is to find the smallest Fibonacci that is greater than or equal to the length of a given array. Let the found Fibonacci be FIB, that is mth Fibonacci number. We use m minus 2 at the Fibonacci number as the index if it is a valid index. Let m minus 2 at the Fibonacci number be I. We compare array of I with x. If x is same, we return I. Else, if x is greater, we recur for subarray after I. Else, we recur for subarray before I. Let array of 0 up to n minus 1 be the input array and element to be searched be x. Find the smallest Fibonacci number greater than or equal to n. Let this number be fib m, mth Fibonacci number. Let the Fibonacci numbers preceding it be FIB mm1, that is m minus 1th Fibonacci number, and fib m2, that is m minus 2th Fibonacci number. While the array has elements to the inspected, compare x with the last element of the range covered by fib m2. If x matches, return index. Else, if x is less than the element, move the 3 Fibonacci variables to Fibonacci down, indicating elimination of approximately rare 2/3 of a remaining array. Else, x is greater than the element, move the 3 Fibonacci variables 1 Fibonacci down, reset, offset to index. Together, these indicate the elimination of approximately front 1/3 of a remaining array. Since there might be a single element remaining for comparison, check if fib mm1 is 1. If else, compare x with the remaining element if match return index. So, time complexity for a Fibonacci search is explanation. Since it divides the array into 2 parts, although not equal, its time complexity is big O of log n. It is better than binary search in case of large arrays 5. So, the main searching techniques are linear search, binary search, interpolation search, exponential search, and Fibonacci search. And the time complexity of a linear search is big O of n. And the time complexity of a binary search is big O of log n. And auxiliary space is big O of log n. Next. Interpolation search time complexity is big O of log 2 of n, and the space complexity is big O of 1. Exponential time complexity is big O of log n, and the space complexity is big O of 1. Fibonacci search, the time complexity is big O of log n. Thank you. This was my PPT and AAT concept video of a course, Design and Analysis of an Algorithm. Thank you.